Hello viewers, welcome to the lecture on conformations of cyclohexane. In the beginning, let us have a brief introduction about stability of different cycloalkane rings. During the 19th century, it was incorrectly believed that cycloalkane rings are planar. The main advocate of this view was the leading German chemist Adolf von Baer. Baer in 1885 proposed a theory of angle strain according to which the difference between the tetrahedral angle of 109.5 degrees and the internal angle of the appropriate polygon is used as a measure of molecular stability. If a cycloalkane requires bond angle other than 109.5 degrees, the orbitals of its carbon-carbon bond cannot achieve optimum overlap, and the cycloalkane must have some angle strain associated with it. A planar cyclopropane with 60 degrees bond angle will have maximum angle strain related to difference between bond angles of 109.5 degrees and 60 degrees. In addition to the angle strain, the bonds in cyclopropane are eclipsed. The Newman projection of cyclopropane resembles eclipsed conformation of propane. The eclipsing of bonds gives rise to torsional strain. The sum of angle strain and torsional strain together constitute ring strain. According to Baer, cyclopentane should be virtually angle strain free, as ring angle of planar pentagon 108 degrees is much closer to the tetrahedral angle than those of any other alkane. Beyond cyclopentane, the cycloalkanes should become increasingly strained as the bond angle increases. The angle of regular hexagon is 120 degrees, and angles of other large polygons deviate more from ideal tetrahedral angle. From experimental point of view, heat of combustion of a ring compound per methylene group, which can be obtained by dividing heat of combustion by the number of carbons of the cycloalkane, is the best way to compare relative stability of different ring systems. Heat of combustion is the amount of energy released when 1 mole of the compound is burnt in excess of oxygen. Baer's strain theory failed when heat of combustion was used to compare the relative stability of cycloalkanes. Cyclopropane has the highest heat of combustion per methylene group, the value being 697 kJ per mole, due to the fact that potential energy is raised by angle strain. Cyclobutane has lesser angle strain at each of the carbon atoms and lesser heat of combustion per methylene group, the value being 681 kJ per mole. Cyclopentane, as expected, has still lower value of 658 kJ per mole. Contrary to Baer's theory, cyclohexane has a smaller heat of combustion per methylene group than cyclopentane. If angle strain were greater in cyclohexane than cyclopentane, the reverse should have been observed. Heat of combustion per methylene group of large rings remains nearly same and similar to that of cyclohexane, rather than rising because of increased angle strain in large rings. The difference in heat of combustion between successive members of homologous series of open chain alkanes is about 653 kJ per mole, which indicates that the bond angle of larger cycloalkanes are not different from alkanes themselves. Thus, prediction of Baer's strain theory that angle increases with ring size is contradicted by experimental fact. The fundamental defect in Baer's theory is the assumption that cycloalkane rings are planar, but with the exception of cyclopropane, cycloalkanes are non-planar. The heat of combustion data shows that cyclohexane has no ring strain, so cyclohexane must have bond angle nearly tetrahedral and have no eclipsing of bonds, the planar ring with bond angle of 120 degree rather than 109.5 degrees implies some angle strain. The planar ring will have some torsional strain due to eclipsing of bonds on adjacent methylene groups. Thus, cyclohexane cannot be planar. In 1895, Hermann Sachs proposed that cyclohexane could exist in two non-planar forms, chair and boat. However, the idea was not accepted at that time as numerous attempts to isolate isomers predicted on the basis of these structures failed. Ernst Mohr, a German chemist, in 1918 extended the Sachs idea and attributed this failure to rapid interconversion of chair and boat forms. The fundamental understanding of the conformations of cyclohexane and the structures of molecules containing cyclohexane ring with electron diffraction and X-ray studies was developed by Ord Hassel and Derek Botten, who shared the Nobel Prize in the year 1969 for the landmark discovery. Now, conformational analysis of cyclohexane systems. Cyclohexane assumes a number of puckered, that is non-planar conformations, the most stable of which is chair conformation. The chair conformation is nearly free of angle strain as all the bonds are 111 degrees and not exactly 109.5 degrees. The increased bond angle causes slight flattening of the ring so that the dihedral angles between adjacent carbon-carbon bonds are 56 degrees instead of 60 degrees. And the vertical CH bonds are not exactly parallel to the axis of the ring but lean outwards from it by 7 degrees. The torsional strain is also absent as all the bonds are staggered. The only steric strain is due to Gauch-butane-like interaction between neighboring methylene groups. The second but much less stable non-planar conformation is called boat. The boat form is relatively free of angle strain as all the bonds are approximately tetrahedral. It is destabilized by torsional strain associated with eclipsing hydrogens on 4 of its carbons. In addition, there is a van der Waals interaction due to crowding between two hydrogens on the ends of the boat on carbon numbered 1 and 4 called as flagpole hydrogens. The boat form is 7.1 kilocalories per mole less stable than chair form. The boat conformation of cyclohexane molecule actually exists as slightly secured twist boat conformation. The boat form is easily twisted so that the flagpole hydrogens move to either side of the molecule, minimizing the torsional and flagpole interaction. The twist boat conformation is separated by another enantiomeric twist boat conformation by an energy barrier of 1.6 kilocalories per mole high, at the top of which is boat conformation. The highest energy barrier in the transition state conformation between chair and twist boat is called half chair. The interconversion from chair to the boat takes place by the footrest of the chair flipping upwards and forming the boat. When the footrest is planar with the sides of the molecule, it is called half chair. The energy barrier for chair to twist boat transition is about double for that of reverse change. Hence, chair form will be predominant in the equilibrium mixture. The population of chair to twist boat is 1000:1 at 25 degrees Celsius. Now, axial and equatorial hydrogens. The 12 hydrogen atoms in cyclohexane do not occupy equivalent positions. In the chair conformation, 6 of the CH bonds, 1 on each carbon atom, are directed alternatively up and down parallel to the axis of the ring. These are called axial bonds. The other 6 carbon-hydrogen bonds make an angle of 109.5 degrees with the axis of the ring, or 19.5 degrees with the horizontal plane of the ring, and are called as equatorial bonds. Each carbon atom has one axial and one equatorial bond, one upward and one downward, and the pattern alternates. Ring inversion in cyclohexane and conformational itinerary of chair inversion. At room temperature, cyclohexane is interconverting rapidly between two identical chair conformations called ring flip or ring inversion. Due to ring inversion, the set of axial hydrogens become equatorial and equatorial become axial. The chair cannot undergo inversion through a planar cyclohexane ring as it involves high energy. According to Hendrickson, the chair form twists to form a transition state conformation called half chair, in which the 4 carbon atoms numbered carbon 1, carbon 2, carbon 3 and carbon 4 lie in a plane with the other 2 carbons numbered carbon 5 and carbon 6, alternatively above and below the plane. The process involves extensive bond angle deformation accompanied by increased torsional strain. With torsional and angle strain, the half chair lies about 10.8 kilocalories per mole above the chair form. Further change leads to twist boat conformation, which does not have any angle strain but suffers from residual torsional strain. The twist boat converts to another enantiomeric twist boat conformation via a transition state boat conformation. The true boat is about 1.6 kilocalories per mole in energy above the twist form. An alternative pathway is possible in which chair is twisted into an envelope-like transition state with 5 of the carbon atoms nearly but not quite in a plane and 6th one either above or below it. This form is only slightly higher in energy than half chair. The conformation leads directly to classical boat, which is slightly higher in energy than twist boat. The transition state for ring inversion in cyclohexane should be considered to be more or less freely pseudo-rotating or twisting forms rather than static structures. In cyclohexane, inversion is so fast that at room temperature, the molecules flip about 100,000 times per second over an energy barrier of about 11 kilocalories per mole. Conformations of monosubstituted cyclohexanes. When one of the hydrogen atoms in cyclohexane is replaced by some substituent larger than hydrogen atom, for example methyl group, the substituent can either occupy axial position or equatorial position. These conformations are in equilibrium as they rapidly interconvert at room temperature. The energy difference between equatorial and axial positions becomes significant so that one lower in energy predominates. Measurements have shown chair with methyl substituent in the equatorial position is more stable conformer. At room temperature, approximately 95% molecules of cyclohexane are in chair conformation, having equatorial methyl group, whereas only 5% molecules will have axial methyl group. Calculations have shown that methyl group is crowded when it is axial than when it is equatorial. One of the hydrogens of an axial methyl group is within 190 to 200 picometer of the axial hydrogens on the same side, that is on the carbons numbered 3 and 5. The distance is less than the sum of van der Waals radii of 2 hydrogens, that is 240 picometer, thus causing steric strain in the axial conformer. When the methyl group is equatorial, no significant crowding is observed. The interaction is called 1,3 diaxial interaction because it involves substituent on the carbon atom numbered 3 if carbon bearing the methyl group was numbered 1. Thus, axial substituent is said to be crowded because of 1,3 diaxial repulsion between itself and 2 hydrogens or substituents located on the same side of the ring, that is on the carbons numbered 3 and 5. The 1,3 diaxial interaction is similar to that in gauge conformation of butane. The axial methyl group in methyl cyclohexane is gauge to 2 of the ring carbons, and when in equatorial position, it is anti to the same nuclei. The gauge conformation of butane destabilizes it by 0.9 kilocalories per mole relative to anti. Therefore, the calculated energy difference between equatorial and axial methyl cyclohexane with 2 gauge conformations should be 1.8 kilocalories per mole. The estimated value is close to experimentally calculated value of 1.7 kilocalories per mole. This proves that the same factors that govern the conformation of acyclic molecules apply to cyclic molecules as well. Thus, 1,3 diaxial repulsion in cycloalkanes are same as gauge conformations in alkanes. The extent of preference for equatorial position depends upon nature of the group. Alkyl groups have greater equatorial preference than polar groups, and for alkyl groups, preference increases with size. Tertiary butyl group has a much larger preference for equatorial position than the other alkyl groups. The interaction between an axial tertiary butyl group and axial hydrogen atoms at carbons numbered 3 and 5 are so large that this group mostly stays in equatorial position. For halogens, as the atomic radius increases from fluorine to iodine, the bond distance also increases, and hence halogens do not differ much in their preference for equatorial position. Now, conformations of disubstituted cyclohexanes. Non-geminal disubstituted cyclohexanes exist as 1,2, 1,3 and 1,4 positional isomers. Each positional isomer exists as 2 possible stereoisomers, cis and trans. Each of these cis and trans stereoisomers show conformational isomerism due to ring flipping. Now, conformations of 1,2 dimethyl cyclohexane. In case of 1,2 dimethyl cyclohexane, there are 2 possible stereoisomers, cis 1,2 dimethyl cyclohexane and trans 1,2 dimethyl cyclohexane. In cis 1,2 dimethyl cyclohexane, the 2 methyl groups are on the same face of the ring. The compound exists in 2 identical chair conformations in which 2 methyl groups are axial and equatorial. The 2 conformations are equal in energy with total strain of 11.4 kilojoules per mole. In trans 1,2 dimethyl cyclohexane, the 2 methyl groups are on the opposite faces of the ring, and the molecule can exist in 2 chair conformations in which both the methyl groups are either axial or both are equatorial. The di-equatorial conformer is more stable than the diaxial conformer by about 11.4 kilojoules per mole. Hence, trans 1,2 dimethyl cyclohexane preferably exists in di-equatorial conformation. Now, strain energy for cis 1,2 dimethyl cyclohexane can be calculated in the following manner. Strain energy due to one axial methyl group is 1.7 kilocalories per mole. The strain energy due to gauge interaction between methyl groups, axial and equatorial, is 0.85 kilocalorie per mole. So, this gives a total strain energy of 2.6 kilocalorie per mole. The strain energy of trans diaxial 1,2 dimethyl cyclohexane is 3.4 kilocalorie per mole due to 2 axial methyl groups. For trans-diequatorial 1,2-dimethyl cyclohexane, the only strain is 0.85 kilocalories per mole due to gauge interaction between methyl groups. Thus, trans-diequatorial 1,2-dimethyl cyclohexane is more stable than trans-diaxial 1,2-dimethyl cyclohexane by 3.4 minus 0.85, that is equal to 2.6 kilocalories per mole, and equilibrium is greatly in favor of the diaxial isomer. Thus, trans 1,2-diequatorial conformer is more stable than cis isomer by 1.7 kilocalorie per mole. Conformations of 1,3-dimethyl cyclohexane. Two stereoisomers exist for 1,3-dimethyl cyclohexane as well. The isomer with methyl group on the same side of the ring is called cis 1,3-dimethyl cyclohexane. The cis 1,3-dimethyl cyclohexane isomer exists in two conformations in which both groups must be either axial or both equatorial. The preferred conformation is the one in which both methyl groups are equatorial. Trans 1,3-dimethyl cyclohexane has the methyl groups on the opposite sides of ring. Thus, for trans isomer, one methyl group must be axial and another equatorial, and exist in two conformers having equal preference. The trans 1,3-dimethyl cyclohexane is more stable than cis isomer by 1.7 kilocalories per mole. Strain energy of cis 1,3-diaxial cyclohexane is due to two axial methyl groups, that is equal to 3.4 kilocalories per mole, plus additional 1.7 kilocalorie per mole due to methyl-methyl interaction, with giving a total of 5.1 kilocalories per mole. The strain energy of cis 1,3-diequatorial cyclohexane is 0, and the strain energy of trans 1,3 cyclohexane due to one axial methyl group is equal to 1.7 kilocalories per mole. Conformations of 1,4-dimethyl cyclohexane. Cis 1,4-dimethyl cyclohexane can adopt two equivalent cis conformations, each having one axial methyl group and one equatorial methyl group, which are in rapid equilibrium with each other by ring flipping. Trans 1,4-dimethyl cyclohexane exists in two conformations in which both the methyl groups are either axial or both are equatorial. The more stable chair isomer is the one with both methyl groups equatorial. The two cis 1,4-dimethyl conformers have equal strain of 1.7 kilocalories per mole due to two gauge interactions of axial methyl groups. The steric strain of trans diaxial 1,4 cyclohexane conformer is twice that of methyl cyclohexane, that is 1.7 multiplied by 2, that is equal to 3.4 kilocalories per mole. And the trans diequatorial 1,4-dimethyl cyclohexane isomer has no steric energy at all, like equatorial methyl cyclohexane. Thus, trans diequatorial 1,4-dimethyl cyclohexane is more stable than cis 1,4-dimethyl conformer by 1.8 kilocalories per mole. The energy difference is solely due to axial methyl group in cis dimethyl cyclohexane. In case of disubstituted cyclohexanes having two different substituents placed at axial and equatorial positions, the one with larger equatorial substituent will be favored. In 1,4 tertiary butyl cyclohexane, one tertiary butyl group should be at the axial position if the ring exists in chair form. Since tertiary butyl group exerts a strong 1,3 diaxial interaction, that the ring is forced to exist in twist boat form. In the twist boat form, the groups are not exactly equatorial as in the chair conformation, but are directed away from the ring and are known as the pseudo-equatorial positions. There are some other factors other than steric which can affect conformational analysis, and we will briefly describe some of them here. Dipole-dipole interaction. In some trans 1,2 dihaloalkanes, the diaxial conformer is sometimes more populated than di-equatorial conformer. The percentage of diaxial isomer increases from chlorine to iodine. In di-equatorial conformer, there is electrostatic repulsion between dipoles as dihedral angle theta is 60 degrees, which destabilizes the di-equatorial conformer, whereas in diaxial conformation, the dipoles are separated as they are oppositely placed. Theta is 180 degrees. The dipole's moment is 0. The relative proportion of isomers in solution depends upon solvent polarity. More polar solvent generally favors di-equatorial form. Effect of intramolecular hydrogen bonding on conformations. Presence of intramolecular hydrogen bonding is a predominant factor in stabilizing a conformation. In cis cyclohexane 1,3-diol, the diaxial conformer is preferred due to intramolecular hydrogen bonding than di-equatorial conformer. Presence of intramolecular hydrogen bonding forces the cyclohexane 1,4-diol to exist in both conformation, thus deviating from the general concept of chair form. In 2,5-ditertiary butyl cyclohexane 1,4-diol, intramolecular hydrogen bonding stabilizes the otherwise high energy twist boat conformation. Conformations of 1,1-disubstituted cyclohexanes. The 1,1-disubstituted cyclohexanes exist in two interconvertible conformations due to ring flipping. When the two substituents are same, as in 1,1-dimethyl cyclohexane, the two conformers are identical. If the two substituents are different, like in 1-ethyl, 1-methyl cyclohexane, the two conformers are distereoisomers and one is preferred over another. The conformation with bulkier substituent in equatorial position often predominates. Usually preferred conformation is less populated than expected, and in some cases the opposite conformation may predominate. In 1-methyl 1-phenyl cyclohexane, the conformer with axial phenyl and equatorial methyl will predominate over the axial methyl and equatorial phenyl cyclohexane conformer. With this, we conclude the lecture on conformations of cyclohexane. Thank you for watching.